Okay, what we are looking at here is internal resistance, and this is a new concept. Hopefully you've looked at the video on resistance. It was a reasonably long one, but it was a goodie. So this is internal resistance. What we haven't talked about in the past is that when you have a source of EMF, voltage, so if I use EMF or E, then I'm talking about the volts. EMF stands for electromotive force. It's an old expression, but you'll still see it used. Electromotive force. They mean the voltage. Strange expression, isn't it? So, but what we haven't talked about is the fact that, this voltage is not a constant. There's a certain amount of resistance, if we call it resistance. Basically, this voltage is an energy producing chemical reaction in a battery, and over a period of time, for example, that battery can have deposits that build up and other things like that, or just a limited amount of chemicals to produce that voltage, and we get what looks like an internal resistance, and we include that internal resistance as a resistor in series. So when we look at a circuit like this, this is the outside resistor, but this is like an inside resistor that we can't actually separate from the battery. That's why we call it an internal resistance. So if we call this V here, the voltage we measure, and we call the voltage on the battery as E, epsilon, or whatever you want to call it, then we've got these two different symbols. V is what we measure, but it's going to be changeable. E might be what the battery can put out, but it only puts that out if there's no current flowing. So when you measure V and there's no current flowing in the circuit, then you pretty much are measuring E. Because what happens is, as current flows, the internal resistance in the battery means you lose some voltage inside the battery, so that when you measure it, it's less than what it would be if there was no current flowing. Let's put numbers on it. So you've got a 12-volt battery, and when no current flows, it's got 12 volts. So E equals 12. As soon as a current flows, and you go to measure it with your voltmeter, you might get V equals 11 volts. This is one of the reasons we make voltmeters with a very, very high resistance. A very high resistance means very small current. Very small current means very low drop in the internal resistance, or very low voltage drop across that, because there's a very small current. And therefore, when we actually measure with a voltmeter and there's no current flowing in the circuit, we will actually get pretty close to the voltage that it ideally would supply. Now, with car batteries, for example, the way to test them is to put a huge current and just see. So if we get a big current flowing here, and we would do that by making this a very low resistance over here, we'll get a big current flow, and if our voltage in a car battery is meant to be 13.2 volts when it's nice and perfect, 6 times 2.2, if it only drops down to about 13 with a big current flowing, right, we know this internal resistance is very low. For example, if the internal resistance was like 0.001 ohms, then 10 amps flowing through it is going to produce very little voltage drop across here, right? And so that would be a good battery. But if you've got a big internal resistance, maybe 10 ohms or something like that, then if you had 10 amps flowing, you'd lose 10 volts, and you'd end up with 2 volts here, right? So internal resistance determines pretty much how good your battery is. So as the battery deteriorates, chemical degradation, chemical buildup, then we get an increase in the internal resistance, and the battery actually cannot supply the voltage. It still would have the voltage, because the voltage is determined more by the type of chemical reaction. So that doesn't sort of drop down to 6. Your output drops down to 6, because as the current flows, you've lost some of the voltage before you even started. So let's do this as an equation. This means that E is actually equal to V plus, so this V plus, so this is the V I'm talking about, the V through this part of the circuit, plus the voltage drop across the internal resistor, which will be the current in the circuit times R. Right? We good with that? So that's our equation. And that little r is the internal resistance. Now you're going to get given various problems to do with that. We can make this a little bit more straightforward. What's V? Well, V is I big R. So plus I little r equals I times R plus little r. Right? So if we want to solve that, we could actually say little r is equal to E minus I big R all over I. It's just an equation for the internal resistance. We can graph this. That's another cool thing that we can do, right? You'll be given a variety of problems. I think you're going to find internal resistance is not too complicated. If we graph this, we would graph current down on this axis and volts on this axis. We would get a line that went like this. Nice linear graph, right? And basically what we're doing, so we would have to actually, to see how that graph goes, let's go back to our formula. Now if I want to graph volts, we've got that, right? What's our independent variable? It's current. So our intercept becomes E, and our gradient becomes negative R. All right? That just shows how that works. So we'll do a variety of problems in class, but that's the theory.